Okay, so we're going to be looking at the derivative, part 4, the last of our little derivative rules. We're going to be looking at the first one here is the inverse trigonometric differentiation. These are some rules that you're going to need to know. And so the first thing I want to do is I want to show you how how one of them came about, so you can see how all of them are done. So first things first, we know that the derivative of the sine is the cosine, but what is the derivative of the inverse sine of x? Okay. Well, to do that, what I'm going to do is I'm going to say, okay, let's let y equal the inverse sine of x. So if y equals the inverse sine of x, then I can undo the inverse part of this thing by taking the sine of both sides. So I get this quantity right here. And then I get the equation sine of y equals x. I can take the derivative of this. And by doing so, actually, let's do this part over here. If the sine of y equals x over 1, then I can make my right triangle. Here's angle y. Opposite over hypotenuse, so that is x over 1. And by Pythagorean theorem, it gives me this quantity right here. Okay? And that's going to be useful for us here in just a moment. I can also come over here and take the derivative of this with respect to x. And so doing, I get the cosine of y times dy dx equals 1. Okay? Solve for dy dx, I get that quantity right there. Okay, pretty straightforward. The next thing then is, well, we can make this connection. So if dy dx, y is the sine inverse, so dy dx is the derivative of the sine inverse of x with respect to x, which is this thing right here. And the cosine of y is adjacent over hypotenuse. And since it's on the bottom, it reciprocals up. I get this quantity right here, which is basically the derivative of the inverse sine. Okay, and so that can then generate our generic rule that you're going to need to know, the chain rule portion of it. And so this is how that rule is how you want to memorize for the chain rule action. Okay, so that's where they come from, and you can do the same argument for all the other inverse trig functions. Okay, so I'm going to show you the rules now. I want to show you some comparison of the rules so you can see it. I want you to look closely at them, and you will notice that these three over here, okay, and these three over here, they differ only by a negative sign. So that and that are this is the negative of that, the negative of that, the negative of that. So if you really just know these three rules and who they are attached to, you can then just know that the negative is the other one. So how do I know which one's the negative? All the ones that have a C are the negative of something. Okay? So the other ones are the positive of those things. So you really only got to memorize three rules and remember to attach a negative to all the inverse trig functions that start with a C. I don't know, a couple ideas might work for you. So let's find that derivative right there. I'm going to move my paper over and we'll go through it. So find the derivative of the arctangent of x to the third with respect to x. Okay, so we have our rule. I'm going to write it right over here. So the derivative of the inverse tangent of u with respect to x is 1 over 1 plus u squared du dx. So we need to find all of these things. And so since our formula uses the u, the inside function, you should identify the u. So u is x to the third. And so since I know what u is, I can easily find du dx by simply taking the derivative of this with respect to x. And so this gives me 3x squared dx by chain rule. All I have to do now is just plug these things in using parentheses right into that formula. So the derivative of the arctangent of x to the third with respect to x is 1 over 1 plus u squared times du dx. U is x to the third, and this is 3x squared. And then all I have to do now is just clean this up. This is 1 plus x to the 6th. And you are done. Sorry, you can see it all. That's how that works. Okay, so let's take a look. Let's see if we have another example coming. Yes, we do. I have that over here. Let me put it on this one right here. So we're doing this one down here. What is, if I tell you that g is equal to this, then what is the limit as x approaches the square root of 3 of that expression? Okay, so what we want to do here is make sure we understand what we're looking at. So when you see these things, don't panic. What is this? Okay, you need to learn to recognize this. This right here is the limit definition of a derivative. So what this thing is actually asking me to do is take the derivative of g. Okay, think back. This is what? A is this number right here. So this is g of x minus g of a over x minus a. So that's that alternate formula. So this is the limit definition of a derivative. So they're really just asking me to find g prime of x. Okay, since g prime of x is this, I'm asking you to find the derivative of the sine inverse of this quantity with respect to x is what I'm asking you to do. And then we're going to evaluate it at the square root of 3. Okay, so that's what we're going to do there, and then we're going to evaluate at the square root of 3. So we have a formula for this. Okay, what was the formula for the inverse sine? If you don't remember what it was, okay, I'm going to write it right here. So our formula is the derivative of the sine inverse of u with respect to x is 1 over the square root of 1 minus u squared du dx. Okay, so that was our formula right there. And so what is our u? Okay, and what is our du? Well, our u is x over 2. Our du with respect to x is 1/2. So based off of this, we can use our formula, and we can write this out as 1 over the square root of 1 minus u squared, so that'd be x over 2, and then times 1/2 du dx. Okay, I'm going to show you how this lays out so you can kind of see it a little bit. At this point, you can actually plug in the square root of 3 if you want, so you don't have to do it twice. That's up to you. Okay, you can work this out and simplify this, and then plug in the square root of 3. Let me just go ahead and show it to you. Once I have the derivative, I can simply go right into this evaluation. So what is this going to be? It's going to be 1 over the square root 1 minus the square root of 3 over 2 squared times 1/2. So as I work this out, you'll see on the bottom you're going to get the square root 1 minus 3/4. If I square this, it'll be the square root of 3 squared and 2 squared. There's the 1/2 again. So what do I have down here? This is going to be 1/4. So I have 1 over the square root of 1/4 times 1/2. So now the square root of 1/4 is 1/2. So this 2 is on the bottom, that's on the bottom. So literally what I have is I have 1 over 2 times 1/2. That 2 is in the front. This became the 1/2, and this is a 1. Okay? So they asked me to find this limit. Since I recognize it as a derivative, I can use the derivative to help me figure that out. And so now I have, in conclusion, so the limit as x approaches the square root of 3 of g of x minus g of square root of 3 over x minus the square root of 3 is equal to, and you're done. Okay? So let's take a look at another example that I have for you. We're going to do this top one right here. Okay. So how do I do a problem like this? Okay. Here is a function or an equation right here, and I need to find dy dx. So how do I go about doing this? Well, here's what I wrote before. So the derivative of this right here, okay, if I take the derivative of both sides, I can do that, okay? But this right here is going to have a y in it. So I kind of, to do this derivative, I got to have it, to do dy dx, I got to know what a y is, okay? Got to get this expression. So what I can do is I can solve this thing for y, okay? So in doing so, I can take this whole thing right here and I can exponentiate it, which basically means raise both sides to the e power, okay? And I get y equals e to the arc cosine of 3x, okay? So if I can solve for y and it's easier to do so, then do so, okay? And so now I can take the derivative of this thing straight up to dy dx because this y is on one side and so forth. So now I can take the derivative of both sides with respect to x. It's a little bit easier in this fashion. So it'll be e to the arc cosine of 3x because the derivative of e to u is e to the u times the derivative of u. So what is the derivative of the arc cosine of 3x? Well, we have our formula. Remember, it's just a negative of the sine one. Okay, so u in our case here is going to be 3x. So keep that in mind. So then this is going to become a negative 1 over the square root of 1 minus u squared times du, the derivative of 3x, dx, which is simply 3. So here is 3x. So as I clean this up, I got a negative on top, a 3 on top, that on top. So I have a negative 3 e to the arc cosine of 3x over the square root of 1 minus 9x squared. And that is a much easier way to do that derivative. Okay. Before we go on to the next example here, we have to now look at higher order derivatives. Okay. So we've been doing what's called the first derivative. I can take derivatives higher order than that. So I can take the derivative of a derivative of a derivative of a derivative and go as high as I need it to go. So the notation for higher order derivatives are basically the same format. I can do double primes for the second derivative. The second derivative with respect to y, right? I'm sorry, the second derivative of y with respect to x twice. Put a little 2 there and a 2 on behind the x here. So after the d and then after the x, I can do a double prime for f, or function notation. This is basically the same as this over here. For a third, I use 3 primes, or the number 3, or 3 primes. And then if I have orders, derivatives higher than that, you just basically do based off of the number. So, and you would use a little parenthesis. So if it was a 4th degree, then it would be y, and then I put a little 4 in parentheses up there. And then you have to put it in parentheses. Okay. Down here, you just put the number, and then again, you got to put the parentheses. We're not going to do too many high order. I mean, we will do, obviously, first derivatives, we'll do second derivatives, and sometimes we might do a third. We usually don't go higher than that. But the first and second derivatives are things we will use considerably in here. Okay, quite a lot. We're mainly going to be dealing with first and second derivatives, as you can see. So with that, let's go learn and do a second derivative and how that works. So here is a second derivative example that I have using the trig function and an e. Okay. So we're going to do, like everything else, we just do our derivatives as we move along. So we have the derivative of y with respect to x. We take the derivative of this, so that's a constant. The derivative of the secant is secant tangent. So this becomes 2 times the secant of x times the tangent of x times the derivative of x, which is just 1, plus the derivative of e to the x, which is just e to the x, times the derivative of x, which is 1. So that is the first derivative. So for the second derivative, we have to take the derivative of this. What is the derivative of the derivative? Well, that is the second derivative of y. We're going to do it again, do it the second time, and we're going to take the derivative with respect to x again for the second time. Okay. What's important about this little future information is I can take the derivative. If I have an equation that has multiple variables in it, I can take the derivative with respect to x, and then I can take the derivative again with respect to a different letter. That's something in the future for you guys. That's why you have to write it this way. All right. Start right here, and you can see that we're going to have what? We got a product rule here. So I have to do the product rule for this term now, and 2 is a constant, so it can be in the front. It is that, and then that. So it is the first times the derivative of the second, and the derivative of the tangent is secant squared of x. Plus the second times the derivative of the first, and the derivative of the secant is secant of x times the tangent of x. And the derivative of e to the x is just e to the x. That is the second derivative right there. You can stop, do whatever you need to do after that. If you need to simplify it, you can do so. These all have a common factor of secant, so I can bring out the 2, the secant of x, and I would have a secant squared of x plus a tangent squared of x left over, and don't forget plus e to the x. So that would be my final answer right there. That is the second derivative. Okay. Ready? Looks like we have another example. Let's go ahead and take a look at it. So what would be the third derivative of this function? All right, well, just one at a time. So what is the first derivative of this function? I have 8x to the third minus 5. The derivative of the sign is the cosine, so it'll be plus the cosine of x. Okay, so then I want to take the derivative again. So now I have 24x squared. The derivative of this is 0, and the derivative of the cosine is minus the sine. And then we do it one more time. This is going to be 48. And the derivative of the sine is the cosine, so it'll be minus the cosine of x. That is the third derivative. Do you notice, like, every time you take a derivative, the power, if it's polynomial stuff, the power lowers by 1 each time? That's kind of nice to recognize that. Look for patterns along the lines when you're doing stuff like this. Here's another one. Find the second derivative of this. This is the trig function. We got chain rule action going on. Start with the first derivative. 8 is a constant, so it can be right here in front. And I take the derivative of the sine, and I get the cosine of that quantity. Chain rule times the derivative on the inside, which is 1/2. Okay? Because you know you're going to do a second derivative, you should clean this up a little bit so that you don't have a bunch of terms all over the place. Okay, so like this number 1/2 and the 8 can come together, and when I have 4 times the cosine of x over 2. You do want to clean up between. It just makes taking the next derivative so much easier. So f double prime of x then is going to be the constant 4 times derivative of the cosine is minus the sine of the quantity, then times 1/2 the chain rule. And there we are. And then I can clean this up, and I'm going to get a negative 2 times the sine of x over 2. And there you go. Okay. I have more to do. That's just more examples. More examples. Here we go. Let's look at that one. Okay. Because I can't really solve for y, I'm going to have to take the derivative implicitly. So let's take that, start us off. This is going to be 2 times y times dy dx equals 7 times dy dx plus 4. Before I go on, I do recommend again that you try and solve for dy dx. Try and do that. If you can't, you'll have to take the derivative as you see it. But it's best if you can solve this for dy dx. I can move the 7 over here and then factor out the dy dx and move things around. And when I do so, I'll end up with dy dx equals 4 over 2y minus 7. Now at this point, I got to take the derivative again, okay? And so I can look at this as a quotient rule, or I can look at this as a product rule by moving the bottom quantity up to the top with a negative 1 exponent. Either way, it's fine. I find this to be easier. If I can do this, I usually do this approach, but you do not have to. So the next part here is take the second derivative with respect to x twice. And so now I do this. Multiply out in front, so I get a negative 4. Take the quantity, lower the power by 1, times, chain rule, the derivative on the inside, which is 2, be careful, dy dx. That's what you got to be very careful on, okay? So when I have this, I got a dy dx in here. Let's take the 2 and the 4 and bring that together, okay? Well, let's take it this way. So let's replace this with what we know dy dx is, which is this quantity right here, okay? So in doing so, this becomes a negative 4 times 2y minus 7, negative 2, times 2 times 4, 2y minus 7 to the negative 1. So this is that, okay? And so now I can bring things together a little bit easier. This is a 4, 8 times 4, negative. This is a negative 32, okay? I have negative 2 of those, a negative 1 of those, so I add the exponents, and I get 2y minus 7 to the negative 3. You can leave it like that, or you can write it without negative exponents, which would be a negative 32, 2y minus 7 to the positive 3. Either way of those two is fine. So the thing here is, remember, if you have this, you got to make sure you do your chain rule stuff every time, and then that, we know the value for that, and we can replace it with the expression that it was equal to. That's why you want to be very careful and clean up your work as you move along. So here's another example we have. Okay, we got an inverse trig function. We want to find the second derivative of it. So let's start with the first derivative. If you don't remember your rule, hopefully you have your rule sitting next to you. This is going to be 1 over 1 plus u squared times du dx. So the derivative of that is 2. And then we can clean this up and get 2 over 1 plus 4x squared. Okay, so now I can come over here. I can look at this differently. I can say, okay, I don't want to do the quotient rule because this is a single number on top, a constant. I can just bring this up on top, and now I have 2 times 1 plus 4x squared to the negative 1. Again, you don't have to. You can do the quotient rule. If you bring it up, you can do the product rule. So f double prime of x is going to be negative 2, 1 plus 4x squared to the negative 2, lower the power by 1, and then times the derivative on the inside, and that derivative on the inside is going to be 8x. And so then our final derivative is a negative 16x, 1 plus 4x squared squared. Okay? Pause the video right now and see if you can do the last example, this example right here. Okay, I'll give you a countdown. Okay, pause it and try and do it your own self. Second derivative, evaluate it at 4, 3, and 3, 2, 1. Okay, so hopefully you found an answer to this. Let's see how you did. So I need to take the derivative of this with respect to x, okay, because I want to get to the second derivative. So starting off, I'm going to have 2x dx dx plus 2y dy dx equals 0, because the derivative of the constant is 0. Okay, moving this along, I'm going to solve for dy dx, and when I do so, I get dy dx equals negative x over y. So that is dy dx. Okay, let's find the second derivative. So I find the second derivative of y with respect to x twice. I have to do the quotient rule. So it is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square. So when I look at this thing, and I want to evaluate this thing at 4, 3, I don't need to simplify this. I can, ahead of time. Might be beneficial because there's a lot of negatives in here. Okay, if I do, I'll get a negative y plus x dy dx over y squared. But since we want to evaluate this at 4, 3, x is 4, y is 3, I can just leave this right here and I can just plug in these numbers. But I have this. How do I plug in 4, 3 into that? Well, that is that quantity right there. So I don't need to substitute that in. I just need to know the value that this is. So I can actually come back over here, take dy dx, and evaluate this at 4, 3. And if I evaluate this at 4, 3, I get a negative 4 over 3. So that is what dy dx is equal to at this point. And so then I can take that and plug it in with these numbers as I plug them in. So negative 3 plus 4 times negative 4/3 over 3 squared. So, and as you work this out, you should get a negative 25 over 27. And there you go. Okay? So, a lot of things happen in those derivatives. You want to take your time, make sure you look at what we did in this video, look at all the different techniques. Now I'm going to show you a second technique for a problem. Take a look at this one down here. Look at this. Find the derivative of this quantity right here. And you notice that there is a bunch of stuff in here with high powers and all that kind of stuff. I would have to do the quotient rule here to do this. I got product rules inside of quotient rules, inside of chain rules, inside of power rules. This is a mess. Okay? How do I deal with this in a if I try to do the quotient rule with this and be very, very careful, this is going to take a lot of room to do. Okay? So how do I do that? Well, you need a new technique. And here is the technique. Okay, let me go back here a little bit. Zoom in a bit. Let it focus. Hopefully we get it in focus. This is called the logarithmic differentiation. Okay? You're going to use this under two conditions, in my opinion. Number one, you have an expression made up of multiplication, division of several quantities raised to powers. That's what we have. Okay? The other time you're going to use it is when the expression has a variable in both the base number and the exponent. There is a base number in an x in the base number, and there is an x in the exponent. When you see something like that, okay, and these expressions can be anything. I can have sine of x raised to the x. There's so many things you can do. You need to do the expansion rules of our logs. So what we're going to do is we're going to take the log of both sides and then use the expansion rules to simplify our work. These are the expansion rules we had in pre-calc. Okay? So you can pause right here and write this all out. and then I'm going to move on. Sorry, put my hand in there. So pause it and write it out. Okay. Let's go back and do our problem. Let's do that problem. So the first thing I want to do is I want to break this up, I have to take the natural log of both sides. So I'm going to take the natural log of y and the natural log of all of this. Okay, I have not started the derivative yet. I will tell you when I start the derivative. Right now I'm just doing manipulations to make it look different. This side is still the natural log of y. Because of the expansion rules, I can take all this stuff in here and split it all apart according to our rules. On the top, there is a 3. Numbers are their own thing. Okay. There's an x base number, there is this quantity base number, and this is on the bottom. Remember, the things on top get pluses, the ones on the bottom get a minus. This is going to be the natural log of 3 plus 4, the natural log of x for that one, plus 5 times the natural log of 2x plus 1. This one's on the bottom, minus 4, the natural log of x squared minus 1. So that is our expansion of this. Okay? If you have any issues about how I got to that and use the rules, make sure you ask in class. Once I have this, now I can take the derivative of this with respect to x, and I can do it with every term separated out, and it's much easier. Okay, what is the derivative of this with respect to x? It is 1 over y dy dx equals the derivative of a constant is 0. This over here is going to be plus 4 times the derivative of natural log of x is 1 over x plus 5 times the derivative of this quantity is 1 over 2x plus 1 times the derivative on the inside here, which is a 2, minus 4 times 1 over x squared minus 1 times the derivative on the inside here, which is 2x. So we've just taken the derivative. Our goal now is to then clean this up and solve for dy dx. So there's a y on the bottom here, so I have to multiply both sides by y. So I'm going to get dy dx equals y times 4 over x. This whole here is going to be what? Plus 10 over 2x plus 1. All this right here comes together as minus 8x over x squared minus 1. Okay? But there's a y here. What does y equal? Y equals all of that. So you need to put all of that back in. So this is going to be 3x to the 4th, 2x plus 1 to the 5th, x squared minus 1 to the 4th, times 4 over x, 10 over 2x plus 1, 8x, x squared minus 1. And that is the derivative. Very, very crazy looking. Okay? But that's how you do it. Logarithmic differentiation with a bunch of product stuff. Okay? I do have one more example that uses this rule. Let's go ahead and look at that now. That was the other example I gave you. X to the sine of x. Same thing as before. If I see something like that, you take the natural log of both sides. X to the sine of x. And then we use our expansion rules and we expand this out so we can break it apart. This is still the natural log of y. This is a power. So that goes out in front times the natural log of x. So that's what it turns into right here. And then I can take the derivative now, and I have a product rule here. So this is going to be 1 over y dy dx equals the first times the derivative of the second plus the second times the derivative of the first. Multiplying both sides by y, I get dy dx equals y times the sine of x over x, and then plus the natural log of x times the cosine of x. And then you can put the y back. X, the sine of x, times all of this. And that's the derivative there. Okay? So that is logarithmic differentiation, and that ends our video for this time. So ask more questions in class.